Let's work through one more example about summing all the labels along a path from the root to the leaf of a tree and then printing out that sum. Some recursive functions build up their result by manipulating the return value of a recursive call, where other recursive functions build up their result by passing information into the recursive call as an argument. And both of these strategies are useful when processing trees. So let's look at an example of both ways of doing things. Before working with trees, let's go back to our old friend factorial. One way to write it is if n equals 0, we return 1. Otherwise, we return n times the result of calling fact on n minus 1. And if we run this example on, say, 4, then we'll get 4 times 3 times 2 times 1 is 24. And this is an example of taking the return value of a recursive call and manipulating it. In this case, we're multiplying in n. But there's another way. Instead, I could define fact times, which takes in both n and k, and instead of returning just n times n minus 1 times n minus 2, this returns k times n minus 1 times n minus 2 times n minus 3 all the way down to 1. And we'll do it as follows. If n is 0, we'll return k, because n factorial is just 1. Otherwise, we're going to return the result of calling fact times on n minus 1 and k times n. And I think what's interesting about this example is that we're not manipulating the return value of this recursive call to fact times at all. Instead, we're just returning it, which means that the result of the recursive call better be the result of the current call. And extending this reasoning, it means the result of the base case needs to be the same result as the original recursive call. And that turns out to be true in this case. So if we're trying to compute k times n factorial, here's the expression. It turns out that's identical to k times n minus 1 factorial. Here's the k times n, and here's the n minus 1 factorial. So here the result is being built up, and by the time you hit the base case, you're done with all the multiplying. Whereas in this version, you haven't done any multiplying at all. When you hit the base case, that all happens after you return. And in fact, if we wanted to define fact in terms of fact times, that wouldn't be too hard. We just return the result of calling fact times on n and 1. Fact 4 is still 24. Okay, now let's work on an example with trees. So I have a file with all of the tree, constructor, and selector functions in it already, called tree.py. So if I want to be able to use all those, I can write an import statement that imports them all. And now I could build a tree. A number tree might look like 3 is at the root, and then we have a branch that's a leaf with 4, and we have another branch that's not a leaf with 5 and 6. And let's have another tree, one with letters in it instead. We'll put H at the root, which has a branch rooted at A, and this will have 2 leaves, the S leaf and the T leaf, and then we'll also have an E, which is its own leaf under the H root. So haste is a tree that has the underlying representation of a bunch of lists within lists within lists, but I can get its label, and that will be H, and I can get its branches. All right, let's say we want to write a function that takes in a tree, finds all the leaves, and for each leaf, prints out the sum of all the labels from the root to that leaf. Much like the fact times function, I'm going to add a second argument, the sum so far, so that I can build up the sum as I go, and then when I get to the leaf, I just print it out. So whether this is a leaf or not, there's going to be a label, and we should add that to so far. But then, we'll figure out if we're at a leaf or not. If we are, then we print out the sum so far, which includes the leaf label and everything above it. Otherwise, we go through all the branches. T is a tree, so I can call branches on it. I get a list of trees, so each B is a tree. And print sums is a function that I can call on trees. So if I call print sums on numbers, starting with 0, I'll see 7. And the 7 came from the 3 at the root, followed by the 4, which is directly below the root and is a leaf. The other thing that should be printed out is the sum along the path from 3 to 5, oh, but 5 is not a leaf, so we don't print yet, to 6. 3 plus 5 plus 6 is 14, which is the 14 we got down here. And what happens when we call print sums on the haste tree instead is that I think we should start with an empty string so that we can add more strings to it, at which point we print out has, that came from H, A, S, and we reached a leaf, or hat, H, A, T, we reached a leaf, or he, which is this leaf below this root. And the structure of this function is that we're building up the sum as we go, always passing a new value into so far. I could have written so far plus label t here instead of this assignment statement, and that would have been fine too. Or we could just update so far and then use the new value either to print or to pass in to all of the recursive calls.